In this lecture session 4, I am going to demonstrate the topic on two transistor model of Thyristor. That means we are going to present the turn-on process of Thyristor by using two transistor model. Here we consider the structure of two transistor model of Thyristor as well as the schematic diagram of the two transistor model. The regenerative or latching action due to a positive feedback can be demonstrated by using a two transistor model of Thyristor. The Thyristor can be considered as two complementary transistors, one PNP transistor Q1 and another NPN transistor Q2. Here we assume this is the basic structure of the Scr model, where the four layers PN and the three junctions J1, J2, J3 and three terminals A anode, K cathode and G gate has represented. And if we can divide this structure by two equal division, then it will take this manner, in which we can say that is PNP or Q1 transistor, that is PNP Q1 transistor, or NPN or Q2 transistor, that is NPN or Q2 transistor. And in the both transistor, the junction J2 is common, that is why junction J2 is common for the both purpose. And IA stands for the anode current, IK stands for the cathode current, and this is the gate current. And this diagram shows the schematic circuit diagram of this two complementary transistor structure, in which we assume Q1 is the first transistor, that is PNP transistor, and Q2 is the second transistor, that is NPN transistor. Additionally, we assume alpha 1 is the common base current gain for Q1 transistor and alpha 2 is the common base current gain for Q2 transistor. As we know, the junction J2 is common for the both cases, that is why junction J2 is common for both transistors. And B1, IB1, that represents the base current of Q1 transistor, and IC1 that represents the collector current of Q1 transistor, and IA that is emitter current, as it is entering to the Scr, which is represented by the anode current. That is why IA equal to IE or emitter current for Q1 transistor. Similarly, IK is the cathode current of the Thyristor. That is why this IK is the emitter current of Q1 transistor. And this is IG, which is called positive feedback. That is why we are injected this IG or gate current towards the device. In general, the collector current IC of any transistor, which is related to emitter current I and the leakage current of the collector base junction ICBO, which is written as IC equal to alpha IE plus ICBO, where alpha equal to common base collector gain, and that can be represented by IC by IE. This is a normal case for any kind of transistor. In this particular case, as we assume two transistors like Q1 and Q2 is there, that is why we can modify that equation like IC1 equal to alpha 1 IA plus ICBO and IC2 equal to alpha 2 IK plus ICBO2. Now the question is, what is IA and what is IK? Just I discussed it before in the previous slide. That is, IA means is the emitter current for Q1 transistor, and IK means that is the emitter current for Q2 transistor. That is why we can represent this term emitter current by IA for Q1 and IK for Q2. Now consider the Q1 as a node, then we can apply the KCL at this particular node Q1, then we will achieve the current IC1 plus the current IC2 that should be equal to IA. That is why we can write the expression like IA equal to IC1 plus IC2. That means we can simplify the equation by using two currents that is defined by IC1 plus IC2. That means we can change the expression and we have taken the value from above two equations. That means IC1 means alpha 1 IA plus ICB1 plus IC2 means alpha 2 K IK plus ICB2. So after simplification, we will get the result that is alpha 1 IA plus ICBO1 plus alpha 2 into IC plus IB2 plus ICBO, this one. So after simplification, we can say IA equal to alpha 1 IA plus ICBO1 plus alpha 2 under common part, that is IC2 plus IC1 plus IG. Okay. So why IC2 plus IC1 plus IG? Actually this expression means actually what? That is IC2 plus IB2. That means we can say ICB2, sorry, that is IB2 means this is IB2 and IC2, that means this is IC2. IC2 means that is again we can say IC2 equal to IB1. So we can replace the equation in this form, that is IC2 plus IC1 plus IG. As we know that is IB2, that means equal to IB2 means it is coming from this current and this current, that can be represented by IC1 plus IG. That is why IB2 can be replaced by IC1 plus IG. That means we can say IC1 plus IG. So again after simplification, we can write IA equal to alpha 1 IA plus ICBO1 plus alpha 2 into IA plus IG. So IA means IC1 plus IC2 plus IC1 that I discussed before. That is IA means that is equal to IC2 plus IC1. That is why we can change the equation in terms of that is IA plus IG. And the remaining part, that is plus ICBO2. So after simplification again we can rewrite the expression that is alpha 1 IA plus ICBO1 plus alpha 2 IA plus alpha 2 IG plus alpha CBO2. Okay. That means just we have simplified this one. So after getting the common part, that is IA, we can rewrite the expression that is equal to alpha 1 plus alpha 2 from the above one, and the remaining part that can be replaced by alpha 2 IG plus IBO1 plus ICBO2. That means we can change the expression from left hand side to right hand side. Then we can say IA into 1 minus alpha 1 plus alpha 2, that should be equal to alpha 1 IG plus ICBO1 plus ICBO2. So the final expression we can write IA equal to alpha 2 IG plus ICBO1 plus ICBO2 divided by 1 minus alpha 1 plus alpha 2. Okay. From this expression we can conclude this the lower or denominator part of the expression, that is 1 minus alpha 1 plus alpha 2. That means if we are increasing alpha 1 or alpha 2, that means the summation of alpha 1 plus alpha 2, if it approaches 1, that means it will give you 0. That means huge amount of current or that means infinity number of the current can flow throughout the device. That means we can say that device is under on state condition. Our approach is we should taken care of this particular current, that is IA. If IA starts flowing, that means we can say the device is under on state. That can be possible by using this equation if alpha 1 plus alpha 2 is approaches near to 1. If alpha 1 and alpha 2 is increases, that means the device will be under latching condition or on state. So let me discuss this in brief. As we know, the current gain alpha that can depends on the emitter current in case of any transistor topology. So we can say the current gain alpha 1 varies with the emitter current that should be equal to IA equal to IE, okay, and which can varies with IK also. As we know, the normal expression IK that is equal to IA plus IG. So why the equation stands for IK equal to IA plus IG? Go to the previous slide. In this case, we can say this IK that should be equal to IB2 plus IC2, whereas IB2 equal to IC1 plus IG, and we know IC2 plus IC1 that will give you IA. That means we can say IK equal to IA plus IG. Okay, so in the similar way, we can say that means IK equal to IA plus IG. That means the typical variation of the current gain, which is replacing by this figure, how the alpha or the current gain can change with respect to emitter current. So here the curve stands for if we are increasing the emitter current, the gain will be increased. On the other way, we can say if the gain in case of alpha 1 for Q1 and alpha 2 for Q2, if the gain is increased, that means the emitter current is increased. That means if alpha 1 is increased, that means IE for transistor Q1 is increased. That means the anode current is increased. Additionally, if alpha 2 is increased, that means which is again reflected on this particular equation. That means again IA is increased. That means total IK or the cathode current will be increased. So we can conclude that if the current IG is suddenly increased, say from 0 to 1 milliampere, this immediately increases anode current IA, which will further increase the alpha 1 and alpha 2. That means the current gain alpha 1, which depends on IA and IG, the increases in the value for alpha 1 alpha 2 further increases the IA. That means it is a kind of cumulative process. Therefore, we can say this is a regenerative or positive feedback effect. That is why alpha 1 plus alpha 2, it tends to unity, and which can be, that means which is able to increase the huge amount of anode current, as the anode current depends on the both gain alpha 1 alpha 2. That means by using that particular equation, that is alpha 1 plus alpha 2, that means that device is under latching condition by applying the small amount of gate pass. Okay. Now talking about the transient case. Under transient condition, the capacitance of the PN junction as shown in the figure here. We know every PN junction has its capacitive effect when we are increasing huge amount of emitter current, or we can say in this purpose that is anode current. That means we can say under transient condition, the capacitor of the PN junction as shown in this figure, which is influenced by the characteristics of Thyristor. If a Thyristor is in blocking state and rapidly we are trying to raise the anode voltage of the device, then it would cause the high current flow through the junction capacitor. And this current to the capacitor, suppose we assume that is suppose ICJ2, okay, and the capacitance of the junction we can assume that is CJ2. So we can write the expression that is IJ2 equal to dQJ2 by dt. Okay, that means Q means that is the junction capacitance plus the voltage across the capacitor, that can be replaced by ddt into CJ2 VJ2, and after simplification or derivative part we can write that is VJ2 into d Cj2 by dt plus Cj2 dVj2 by dt. So see the expression very carefully, in which the junction capacitor is always constant. Actually, it depends on the doping concentration of the layers, and which is normally specified by the manufacturer. That is why we can say, if the junction capacitance is constant and the constant of derivative, that will give you 0. That means we can say the total junction current that depends on the rate of change of voltage. So we can say where Cj and Vj2 are the capacitance and the voltage across the junction J2, representing Qj2 and the charge in the junction. If the rate of rise of voltage dVdt is large, then the junction current that is defined by Ij2 would be large, and this will and additionally it would result in the increasing leakage current. That means ICBO will increase for transistor Q1. Additionally, again it will be reflected for the transistor Q2. That means increment of the leakage current, that is ICBO2. Accordingly, the equation 2 just we have discussed before, the high enough value of the ICBO and ICBO2 may causes alpha 1 plus alpha 2 tending to 0, and results then a huge amount of anode current starts flowing throughout the device or thyristor. However, the large current through the junction capacitance may be damaged the device permanently. So that means we cannot change the anode voltage very frequently or suddenly, as it can damage the junction capacitance. That is why we can increase gradually the anode voltage. That is why we can increase the internal leakage current of Q1. Additionally, the internal leakage current of Q2, that is defined by ICBO1 and ICBO2. That means if the both leakage current will increase, that will contribute the high gain for alpha 1 in case of the Q1 transistor and alpha 2 in case of the Q2 transistor. If the additional gain alpha 1 plus alpha 2, which will tend to unity, that means the expression that I know, that is the denominator part alpha 1 plus alpha 2 is increased, that means the total current is increased. That means we can conclude that if we are injected the small amount of gate current, then the device will be under conducting state. The whole thing that is represented by the two transistor model, due to which this is well defined by the turn-on process of the thyristor by using two transistor model. Okay, thank you.